Hi everybody and kia ora, welcome. This is our final session covering our world-leading research on the use of waste plastics in asphalt. Today we'll be focusing on the results of the performance assessment of low melting point recycled plastics in asphalt and reclaimed plastic modified asphalt. This will include their emission and microplastic release characteristics. We have more than 300 people registered for today's session, so welcome to you all and thanks so much for joining us. So if you're a regular at Austroads webinars, you'll notice that I'm not Ekaterina Kolobrovova. My name's Elena Gardner and I'm the Communications Manager at Austroads. Ekaterina is actually on jury duty until the end of the year, and so while she's away, I'll be your moderator on the webinars. I'm going to be assisted today by the Project Manager, Andrew Papakostas, and Andrew will be moderating the Q&A at the end of the webinar. So I acknowledge the Treaty of Waitangi and Maori as the original people of New Zealand. I also acknowledge the Australian Aboriginal and Torres Strait Islander people of the custodians of the land from which we're broadcasting today. Austroads is based in Sydney, and so today I'm on the land of the Gadigal people of the Eora Nation. Aboriginal trade and travel is woven into the shape of our road network. Some of our major roads were Aboriginal songlines and were important trade routes that crisscross the country. Austroads is based in George Street, which follows an Aboriginal trading route between the rich fishing areas on the harbour, the fresh water stream that was known to the early settlers as the Tank Stream, and farmed grassland to the west. I pay my respect to elders past, present and emerging, and your deep connection to the land. So a bit about Austroads. We're the collective of Australasian transport and traffic agencies, and that's the organisations that are listed on this slide. Our focus is to support our member organisations to deliver an improved road transport network. So today's, the project that we're talking about today was delivered under the Transport Infrastructure Program, and that program is managed by Ross Guppy. So a bit of housekeeping. Today's presentation is going to run for about 60 minutes, and then we'll have a Q&A session that will run for 15 minutes. The slides and reports today's presentation is based on can be downloaded from the handout section on your sidebar. You'll find that over on the right-hand side of your screen. If you have any questions for the Q&A, please send them through as the webinar runs along. If you can, if your question relates to a particular slide, please include the number of that slide in your message, and you'll see the slide number down on the right-hand side, bottom right-hand side of the slide. We have a lot of slides today, about 70, so it does really help us if you can identify that slide number. Just helps us answer the questions the best that we can. If you're having any technical problems, do let us know via the question bar. But just a quick tip, if you lose sound or your picture freezes or your picture just disappears, that issue is most likely with your connection. So closing your browser and rejoining the session via your email registration usually helps that issue. Also, this session is being recorded and it will be available on our website, and we'll email you all to let you know when that's available. If you listen to podcasts, it also will be available on the Austroads podcast, and you can find that in your podcast app by searching for Austroads. And sorry, I'm just having a little bit of trouble with my slides today. Let me bring up my speaker notes. Here we go. Okay, so we have 5 excellent presenters today. The first presenter is Andrew Papakostas. Andrew is the Principal Engineer, Pavements, Geotech and Materials at the Department of Transport, Victoria. Our second presenter is Associate Professor Filippo Giustozzi. Filippo is leading the Intelligent Materials for Road and Airport Pavements Research Group at RMIT University. We are also joined by Yoongjai Boom, a Civil Engineering PhD student at RMIT University, and Dr. Marie Enfront and Dr. Dai Lu Xuan, postdoctoral research fellows at RMIT. So today's agenda, we'll first hear from Andrew, who's going to introduce the project. Then Filippo will take us through laboratory testing of incorporating recycled plastics into asphalt via the mixed method. We'll hear about emissions from plastic modified asphalt presented by Yung, followed by Marie, who will talk about microplastics release from plastic modified asphalt. Di will focus on future recyclability of plastic modified asphalt, and the presentation will then be concluded by the summary of project findings from Filippo. So welcome everybody, it's great to have you, and we're going to hand over to Andrew for an overview of the project. Andrew.
Hello everyone, and welcome to this fourth and final webinar presenting the outcomes of Austroad's project 6305, use of road grade recycled plastics for sustainable asphalt pavements. Now the project is being delivered by Austroads with funding provided by the Transport Infrastructure Council. Now a reminder that the primary aim of the project was to identify road grade recycled plastic that can be used in the construction and maintenance of asphalt roads. The project team is made up of an advisory board consisting of Austroads, road agency and industry representatives, which was established to provide project oversight and direction. The Austroads Pavement Task Force, also consisting of representation from Australia, New Zealand road agencies and industry, was established or was used to provide technical advice, support and review. And most importantly, the last component of the team was the RMI research team led by Filippo. Next slide, please. So today's webinar presents findings of the remaining comprehensive testing that was completed and recently published in report number 3B. Now, all reports and previous webinars are freely available from the Austroads website. I now hand over to Filippo to provide the outcomes of the remaining testing that was undertaken and reported in report 3B. Thanks, Filippo.
Thank you, Andrew. Just share my screen. Yeah, thank you, Andrew, and good afternoon, everybody. Today I will be presenting on the final incorporation methods that we have been put together during the Austroads project, which we call the mix method. Just a quick overview about what the mix method is about. In the previous webinars, we have presented about the wet method, so bitumen modification, and the dry method, where we were using plastics as an aggregate replacement. So in today's presentation, the mix method is actually a combination of both. The plastic is added directly to the pug mill or to the aggregates, to the hot aggregates, in order to create a polymer modification or a coating of the aggregates, a polymerized coating of the aggregates first before the bitumen is actually added afterwards. So for these reasons, we need to look for plastics that is actually capable of melting around that mixing temperature of 160, 170 degrees Celsius. So we're looking at low melting point plastics. The two types of plastics that we selected, and again, if you missed the previous webinars, I may point you towards the report number 1 and number 2 specifically, which, as Andrew said, are freely available for your download through the Austroads website. There is an explanation there of how we ended up selecting these two groups or subgroups of plastics. The one on the left-hand side is a recycled form of polyethylene, low-density polyethylene coming from a post-industrial stream. The one on the right-hand side is a commingled version of polyethylene and polypropylene coming from post-consumer streams. If you look at the characteristics of the plastics in the table, you will see everything from the composition, so in terms of how much LDPE, how much LLDPE, so the linear low density version of polyethylene, and their respective melting points, density, and a little bit of standard properties of these plastics. But as I said, you will find all the details in report number 2. Just a quick video in terms of how the mix method actually works. It may be a bit laggy at your end, but I think Austroads has provided you with the video in the hands-out materials. So you've seen there plastics being added to the aggregates only, and after a thorough mixing, then basically the plastic has disappeared. This is what you get at the end of the mixing between aggregates and plastics before adding the binder. And then after this step, everything goes on according to the standard mixing operations. So if you want to see a few pictures about this process, at number 1 on the left-hand side, these are the aggregates in the mixer. Number 2, we just added, in this case, it was the commingled version of polyethylene and polypropylene you've seen before, onto the hot aggregate. And then number 3 is actually the final product of the plastics melted around the aggregates before the bitumen is actually added. So if you zoom in on number 3 and you isolate one particle, this is actually how it will look like, where you have an aggregate and the aggregate may or may not be coated with recycled plastics. So this is the mix method procedure. In terms of mix designs, we have been using neat C320 binder, bitumen, and if you are joining us from other countries outside of Australia and you're not familiar with the classification grade, a C320 binder can be something similar to a 50, around 50 penetration grade, and you can see all the values in that table down at the bottom. The binder content was 5.1% by mass of the mix, and we have used 3 different dosages of recycled plastics at 0.5, 1, and 1.5% by mass of the aggregates. I'm going to show you in the next few slides why a maximum limit of 1.5% was put for this particular experimentation. We also compared the mix design at 0.5, 1, and 1.5% plastics with standard conventional polymer modified binders, specifically an A35P, which again, if you are outside from Australia, is a combination of 5 to 5.5% EVA polymer. And we compared the results also with unmodified C320. The aggregate gradation was that of a wearing course. The mix design was registered in Victoria. The maximum nominal aggregate size was 14 millimeters. This is how the compaction curves look like. And the black curve is actually the way standard conventional asphalt is compacted. So you have the air voids on the y-axis and the number of gyrations on the x-axis. And if you focus on the blue lines, these are the ones related to the post-consumer type of plastics at 0.5%, 1.1%, 1.5%, and then 2%, represented here in red. That was kind of our maximum limit, and we have excluded that from the experimentations, as I said, because it was quite tough to compact. I will show you a video in a second. But depending on the type of plastics, you may have 2 different behaviors. So if you look at the green curves here in this graph, they were quite easy to compact up until a certain point where the curve will start becoming a bit horizontal. So you really need a little bit of extra energy to make sure that the void content goes down. But actually, we found that they were quite compactable when we were using the RLDPE, so the post-industrial type of polymer. When using CPEPP, because of the polypropylene content and the high or the higher melting point of polypropylene at around 160 degrees, that will probably be tough to compact compared to the other. Now, this is a very quick example of how different mixes are at the end of the manufacturing process. So the video that is running now is related to a low to medium plastic content. And you can see that it's quite flowable and workable, and it was very easy to compact. When you start adding more plastics, you will see that it becomes increasingly more difficult to work with and to handle. Still workable, but obviously more effort is needed. and that will translate in more compaction effort to achieve the void contents in the field. At the last video here, number C, is related to an excessive plastic content, and this is exactly that 2% mix that I showed you before in the previous slide with the red curve. You can see that actually you cannot really work with that at all. You have big chunks of asphalt, so it was quite difficult to handle. Just to give you an idea about the different dosages and how they translate into compactability or into the densification behavior. Now, in terms of moisture damage, we looked at the tensile strength ratio of the different mixes. In the blue zone here, you have the post-industrial plastics. In the green zone, you have the post-consumer type of plastics. Well, the first thing to notice is that within the post-industrial plastics, the results was quite consistent and I would say high, above 80%. Usually in Australia, 80% is kind of the threshold value for assessing the tensile strength ratio. Obviously, there is an increase in the dry tensile strength of the mix. This was also observed in the green zone for the other type of plastic, so an increase in the in the dry tensile strength of the mix. But obviously, you can see that the TSR value goes down all the way to 64.6%. And that, as I said again, probably is related to the high melting point of the polypropylene that doesn't fully melt when added to the aggregate. So maybe higher temperature, longer mixing time will fix this. In terms of rutting, the mix method is probably very good and probably much better than the other two methods we've been discussing in the past webinars. This is the rut depth of standard asphalt, and these are the other mixes that we've tested. Now, just to give you a bit of a better overview and provide some more details, I've plotted here the reduction in rut depth compared to the standard unmodified asphalt. You can see that as the conventional polymer modified binder A35P with 5.5% of EVA, it's actually reducing about 79% rutting compared to the conventional unmodified asphalt. And 1, 2, and 3, so the 1%, 1.5%, and 1.5% CPEPP are actually reducing rutting even more than the A35P. So it is quite good in terms of resisting rutting. When it comes to fatigue, we've also found that depends on the type of plastic that is being added. If you focus on the fatigue charts on the right-hand side and you look at the green curves are related to the post-consumer plastics. The more plastics you add, usually the better fatigue you get. But there is really a big difference between the green curves and the gray type of curves, which are instead related to the post-industrial plastics, 0.5% RLDP, 1%, and 1.5%. The black line is the conventional asphalt mix, so unmodified. The red line on at the top of the chart is related to the conventional polymer modified asphalt. And you can see that for 1.5% RLDP, the fatigue performance is quite similar to the one of a conventional polymer modified asphalt. You can see the number here, but you can go anywhere from an improvement of 27.6% compared to conventional asphalt, all the way up to 154% when using 1.5% RLDP. So this methodology is quite effective in reducing rutting, and if you select the right type of plastic, it can also be effective in terms of enhancing fatigue and durability. So concluding the asphalt assessment, and you will find many more data sets in the full report. You will find resilient modulus, you will find cracking tolerance, and many other parameters there. But to keep it within the 60 minutes, we have to cut down something. Concluding on this part, the mix method provided significant enhancements, much more than the other two methodologies. The type of plastic obviously is important. I show you the difference between RLDPE and the commingled version of PEPP. be aware that that can be an effect on the densification behavior, so on how easy it is to compact, depending on how much plastic you use and depending on the type of plastics you're using. Rutting was definitely improved, and in 3 out of 6 cases, so 3 out of 6 plastic modified mixes actually were better in rutting compared to the A35P, the conventional polymer modified asphalt. Fatigue resistance was also improved, as I said, between 27 and 153% extra fatigue life compared to unmodified asphalt. And in 1 case out of 6 mixes, there was comparable fatigue resistance with conventional polymer modified asphalt. So you're saying that out of the 2, probably the RLDPE was better. That was probably because the mixing temperature was equal between the 2 of them. Probably if there is addition of plastics that contains polypropylene, it may be suggested to increase the temperature a bit higher compared to whether there is only polyethylene in it. One type of recycled plastics, the commingled version, seems to suffer from moisture damage, as we showed you through the TSR ratio. I'll now hand it over to Yongjia to talk about the potential emissions from asphalt.
Okay. Thanks, Filippo. Good afternoon, everybody. I will be discussing on the potential emissions from asphalt containing low melting point recycled plastics, or as we call it, the mixed method. So first up, a little recap as we revisit these images here. The plastics that were selected, as mentioned by Filippo, for the mixed method are the recycled LDPE and the CPE/PP.
Yeah, I'm sorry to interrupt. We just can't see your slides at the moment.
Right. Is that better?
Yeah, they're just not on slideshow view. And we've just lost them again.
Just quickly. Can you see it now?
No. Do you want me to? I might just throw the. Oh, there we go. That's it. Perfect. Well done.
Right. Sorry about that. Anyway, I'll jump right in. Just to recap, as we revisit these images, recycled LDPE and commingled PE/PP were selected for the mix method. And basically, the idea here is that upon contact, the plastics would melt and form a layer of coating over the aggregates, and some of them will stay as a solid part of the aggregates until where hot bitumen is added into the mixing process and to combine and produce the actual asphalt mix. And do note that specifically for the emissions test, each plastics were added in individually to form specific blends. In no instances where we would actually use 2 plastics at the same time to create an asphalt mixture. And as described in the previous webinars and also in the report, the fume generation mechanism used for this study employs a temperature-controlled automatic asphalt mixer, or a pug mill, and personal air sampling pumps, as you can see circled in red, are attached to a fabricated lid that sits on top of the opening of the asphalt mixer. All asphalt blends were produced over a mixing period of 15 minutes, during which the air is captured throughout the entire process via these pumps. The measurement for PAHs and VOCs uses XAD-2 tubes and PTFE laminated membrane filters and charcoal solvent tubes for VOCs. These basically, after the sampling process, these solvent tubes and filters were then brought to the lab and extracted via a solvent extraction method and then injected into a gas chromatography mass spectrometer, or a GCMS for short. And basically here again is the full list of the analytes that are being quantified by the GCMS analysis. In total, we are looking at about 48 VOCs and 16 PAHs, of which 9 are known irritants and 5 that are carcinogenic. Reason being that by including a large variety of analytes, we are able to expand our knowledge in understanding the actual effects of recycled plastics and what it does from a work health and safety perspective. Specifically, the benzene from the VOCs and benzoapyrene on the right-hand side, PAHs, they are 2 analytes that are heavily monitored in the work environment, hence their inclusion in this study. A deeper analysis was conducted for each of these analytes to kind of understand if using recycled plastics would either increase or decrease the possibility of these carcinogens. And as usual, a range of testing variable combinations that were conducted for the mixed method. The plastic content ranged across 0.5%, 1%, and 2% by mass of the asphalt mix, while the working temperature ranged from 140 degrees, 160, and 180 degrees Celsius. And do note that the asphalt mixes containing CPE/PP were only conducted at 160 and 180 degrees, as the plastics itself has a higher melting point than 140. Therefore, it was not considered. And as for the recyclability study, which Dai will get into in a moment, the RAP or PRAP content was fixed at 30% by mass of asphalt mix and produced at one temperature at 160 degrees Celsius. In total, we are looking at approximately 40 asphalt mixes for this study segment. Now on to the results. The graphs plotted here basically show the concentrations of VOCs on the top and PAHs at the bottom against plastic content work across all 3 working temperatures. All results are compared to C320 bitumen, represented by the solid black line, and A35P by the dashed line. If you do not already know, C320 is a standard bitumen used in the industry with no content of recycled plastics, while A35P is a commercially available modified bitumen. And it's no surprise that the higher working temperature increases overall emissions for both VOCs and PAHs. I mean, if you look at the 3 different columns, you can already see a spike as the temperature goes up. Increments up to about 100% for VOCs and about 200% for PAHs when temperatures were increased from 140 to 180 degrees Celsius. However, though, from a plastic content perspective, as plastic content is increased, we also see a difference in emission concentration output. Comparing the emissions obtained from C320 at 180 degrees Celsius, reduction rates go up as high as 30% and 20% using VOCs. In VOCs using recycled LDPE and CPE. And from a PAH perspective, the reductions were there, however, not as significant as the VOCs, and the reductions were up to about 13% and about 8% for 1.5% RLDPE and CPE. And as mentioned earlier, a specific compound analysis was conducted to gain further insights on the effect of recycled plastics towards the 2 main selected carcinogens. The graphs here basically show the percentage difference against C320 or HMA And so basically what that means is that if the bars are plotted in a downward direction, it just means that they are in a reduction against C320. In contrast, if a bar is plotted upwards, then it basically just means that there was an increase. But in this case, all bars are directed downwards only. With increasing plastic content, we see an increase in reduction for both benzoapyrene and benzene levels. Specifically at 160 degrees Celsius in gray, we see the largest reduction of these carcinogens by about 40% and about 20% using recycled LDPE and CPE. On the other hand, benzene levels were reduced by up to 20 and about 15% as well on the right hand side. And I guess it's quite important to point out that while these reductions are here, it's also important to remember that benzene and benzoapyrene only accounts for about 0.1 to 0.4% of the total emitted compounds. So although the levels were decreased by 15% as I mentioned earlier, it sits on a different scale of magnitude when compared to the current threshold. Essentially, what we're getting is about 2 to 8 micrograms per cubic meter, which is the measured concentration, versus the workplace threshold of 200 micrograms per cubic meter over a 15-minute period for benzene. To summarize the differences in the different incorporation methods, a graph here is plotted from basically all of the asphalt mixes, including their respective benchmarks. All recycled plastic modified asphalt mixes showed a lower PAH concentration values compared to their respective benchmarks. Note that the wet method is meant to be compared against C170, while the dry and mixed method is meant to be compared against C320. Basically, at a glance, we can see that A15E and A35P, that are two commercially available polymer modified bitumen, using those bitumen to create the actual asphalt mixes, they exhibit lower PAH concentration levels compared to all wet and mixed method. And on the other hand, the dry method asphalt mixes using ABS and PET showed the lowest PAH concentration, followed by the mix and the wet. From an environmental point of view, I guess, what you could get out of this is basically that recycled plastics can still reduce overall PAH emissions compared to conventional methods using C320 and C170, just not as effective as A15E and A35P. From a VOC perspective, C170 and C320 asphalt also exhibited higher levels of VOCs compared to their comparison methods. A15E and A35P asphalt showed quite similar levels to 0.5% plastic content for the dry and mixed method. And in some instances, the dry and mixed method, in the dry and mixed method, higher plastic content led to a higher reduction of VOCs compared to A35P and A15E. So I guess there are basically endless ways of interpreting these results. But if there was one takeaway message from today, is that recycled plastics do in fact reduce emissions from an asphalt perspective. And based on these results, we can conclude that the effect of working temperature plays a significant role in determining the overall emissions, regardless of plastic type or content. The use of recycled plastics, regardless of their type, can reduce both PAH and VOCs, as mentioned earlier. But the plastic content itself will be the determining factor. And finally, a compound analysis is suggested to be conducted in order to understand from a carcinogen perspective on what the actual recycled plastics may cause. And I guess when going through the emission studies in this or any other previous reports, it's quite important to note that bitumen from different sources will produce different emission levels. Therefore, the measurements in this study cannot represent all bitumen and asphalt in the industry. And the lab-generated fumes in this study are presented as a worst-case scenario, and they cannot be used as a replacement for on-site testing. And finally, the objective of this study was to investigate the effects of recycled plastics compared to conventional methods. Therefore, it cannot be considered as a toxicological assessment. And I shall pass on to Marie to finish off. Thank you.
Thank you, Youngja. So after looking at the emissions from plastic modified asphalt, we had a look at the release of microplastics from plastic modified asphalt. So why microplastics? Well, if you think about it, when a road is laid and open to traffic, road dust is generated. This road dust can be made of many different materials, such as truck and car tires, construction materials from nearby construction sites, organics, road marking materials, and of course the materials coming from the road itself, being bitumen and the aggregates. So now if we think about adding recycled plastics into roads, then microplastic could also be released in road dust. So the question is, can microplastics be released from plastic modified roads? In order to answer these questions, we developed a new procedure, and we used a new testing machine called the wet track abrasion machine. So this abrasion machine works by using a rotating head, as you can see here, which is in contact with an asphalt sample, and this is used to simulate abrasion as it would occur on the roads with the cars. This is just a top view of what you can see from the top part of the machine. So you can see the asphalt sample that is maintained here in the pan, and it is covered with water. The reason for using water is because the particles released due to abrasion needs to be collected in the water. If there was no water, they could just be spread across the air and we would lose a lot of particles. The second reason is to prevent overheating of the asphalt sample. And you can guess that below the rotating part here, there is an abrasion head, which is made of metal. And this is what we use to generate abrasion on the asphalt sample. So here, there are different parameters to optimize before finding the optimum abrasion procedure. The first one was the temperature. At which temperature do we need to run the test, for how long, and also at which pH, because we're using water here, so we're able to vary the pH. So after running several combinations, we found that the optimum parameters to run the abrasion test was 60 minutes at a pH 7 and at 25 degrees Celsius. So to maintain a temperature of 25 degrees Celsius, we placed the abrasion machine into a climatic chamber. But that was the easiest part. The hardest part was actually to extract the microplastics from whatever was released from the asphalt sample. And this is how we did it. So here's two pictures of an asphalt sample before abrasion on the top and after abrasion at the bottom. And you can clearly see here that the aggregates are starting to show up this normal bitumen coating on top. So that means that residues were definitely removed from the asphalt sample. And this is what it looks like afterwards. It's basically dirty water, blackish water. So what we did first was to extract the particles from this water through a series of filters. And after that, we got a clean water on this side and dry particles on the other side. These particles were actually a mixture of bitumen, aggregate, and microplastics. So the next question was, okay, we got the dry residues, but now we need to extract the microplastics from this mixture. So we designed an extraction procedure that I will describe to you quickly now. So the first step was actually to remove the bitumen particles from the mixture by using an organic solvent. Once the bitumen was removed from the mixture, we use another organic solvent to separate the aggregates at the bottom from the plastic at the top by density separation. So the density of the plastics was much lower than the density of the aggregates, and they were therefore floating in this solvent. So we're able to recover the particles, the plastic particles on one side and the aggregates on the other side. As for the bitumen, we simply had to evaporate the solvent that we used to dissolve the bitumen to recover the bitumen residues. And thanks to this protocol, we were able to determine the mass of microplastics as well as their size, the mass of aggregates, and the mass of bitumen. So I know that it's only a schematic and drawing, so I've just prepared a video for you to show you the principle of the density separation. So this is not what I did, what I used to extract the microplastics from the residues, but this is an example to show you the technique. So I made here just for you a mixture of LDPE and aggregates, and I then added the organic solvent that I used for density separation. So in that case, dichloromethane. And what you can see is that the black particles, they start floating straight away. And the black particles are actually polyethylene particles. So what you end up with at the end is aggregates settling at the bottom of the beaker and polyethylene floating at the top of the beaker. So this is the principle that I use to extract the microplastics from the residues. So now let's have a look at the asphalt samples. So in the previous report, in previous webinars, I presented you the release of microplastics from asphalt modified with plastic via the dry method and the wet method, where the plastics were either used as aggregate substitutes, they were spread like this in the asphalt sample, or with the wet method, they were spread within the bitumen matrix, so they were spread even more differently in the asphalt. But today I'm going to show you the results of the release of microplastics from the asphalt modified via the mix method. And as Filippo and Yongja mentioned, the plastics are actually used as coating around the aggregates, and they can also diffuse partially in the bitumen. So as I said, the release of microplastics from these samples were presented during the previous webinar. So if you're interested, I invite you to have a look on our website. But now we're going to focus on the release of microplastics from this sample here. Okay, let's have a look first at the release of residues. When I say residues, it means aggregates and bitumen and microplastics. So as you can see here, when the asphalt is modified by CPEPP or RLDP, the trend is different in terms of residues. So it means that compared to a C320 reference where there is 0% of plastic, using CPEPP and increasing the content of CPEPP actually worsens the release of residues, whereas using RLDP reduces the release of residues. So using RLDP actually improves the adhesion between the bitumen and the aggregates, contrary to CPEPP. And if you remember the result that Filippo showed you, this is actually consistent with the TSR results, where using CPEPP actually worsens the tensile, reduces the tensile strength ratio compared to RLDP. Now let's focus on the microplastics, which is the main focus of this talk. So microplastics only, no bitumen, no aggregates. Looking at CPEPP and increasing the plastic content in asphalt, the amount of microplastic is increasing with the plastic content. Whereas when we use RLDP, it is increasing up to 1%, but then the release of microplastic is constant. And if you compare that to two different benchmarks, so A35B and A50, the same as what Yongja used during its emission study, you can see that actually none of the asphalt mix releases more microplastic than the A35B. And actually, most of them release less microplastics than the A50 benchmark, which is good. But there is still a difference between the two plastic mixes, right? And that can actually be due to unmelted or poorly melted CPU particles in the asphalt mix that could cause weakness points in asphalt. And that can also be due to the initial particle size and shape when it was mixed in asphalt. If you remember the video that Filippo showed you, they used CPP as an example, which was made of colorful but irregular plastic fragments, whereas RLDP was very regular and spherical or in the form of pellets particles. So this could also have played a role on the proper mixing of CPPP and RLDP. So here to make those mixes, we use the same mixing conditions and temperature, but of course modifying this could have led to different results. But with these conditions, CPPP can create weakness points in the asphalt. So now let's have a look at the size of the microplastics, because you may know that the size of microplastics can impact their toxicity when they are released in the environment. So the microplastics released from CPPP are going to be shown on this side and RLDP on this other side. First fraction of microplastics that we recover is the smallest one, so between 0.5 microns and 2.7 microns. Here you can see that there is 3%, 11%. It is quite similar between the two asphalt. Now let's move on to the second largest size fraction of microplastics. It is a bit higher for RLDP modified asphalt. Third fraction, similar between the two, and last fraction, the highest is for CPPP. So what do we need to understand from these two schemes, where microplastics released from CPPP are much larger than those released from RLDP microplastics, with almost half of them larger than 300 microns, whereas here most of them are in between 2.7 and 38 microns. And that is actually consistent with the fact that some of the CPPP plastics particles may not be properly melted in the asphalt, which leads to a higher rate of microplastics. So now something maybe you were curious about, what do microplastics look like? Well, this is the answer. So I took pictures with an optical microscope of the plastics that I recovered on metal mesh for these two size fractions here, and on filters for the last two fractions. So let's focus on the first two fractions first. You can see that the size of the microplastics is very irregular, and that in both asphalt modified, plastic modified asphalt, all the particle sizes are found. So it means that you can have large particles, medium-sized particles, but also small and even smaller particles. What you can see on the pictures on the right-hand side are pictures taken with a fluorescence microscope. That's why the particles appear as green dots. But it shows that also very small particles can be released from both asphalt mixes. So what do you need to remember for this result? Well, first of all, RLDP improves the adhesion between the bitumen and the aggregates when incorporated in asphalt via the mixed method, contrary to CPPP. And this is consistent with the TSR testing that was done on the asphalt samples. CPPP can be poorly melted when mixed with asphalt, depending on the direction of the mixing and the temperature used. And that can lead to weakness point in the asphalt, which therefore increases the release of microplastics from this asphalt mix. Finally, the size of the plastics and the shape can also impact their incorporation in asphalt, and therefore that is something that must be monitored and controlled. But overall, RLDP and CPPP modified asphalt mixed method released similar microplastics than the benchmark A35P and A50 that we used as references. Now let's have a quick look at the method that we investigated throughout this project. The first method, was the wet method, and with the wet method you can see that there are different trends in terms of microplastics released, but a low plastic content can lead to a high release of microplastics due to the poor adhesion between the bitumen and aggregates, whereas high plastic content also releases a high amount of microplastics due to phase separation. For this method, an optimum dosage of 2 or 4% of plastics reduces the release of microplastics. For the dry method, only ABS used a low plastic content releases high amount of microplastics, and this was mainly due to the size of the ABS particles that we used in asphalt. Regarding the mixed method, the results that I just presented you, where RLDP clearly releases less microplastic than CPPP, and that's because CPPP can be partially melted in the asphalt. And if we compare that to the two benchmarks that we used since the beginning, well, all the asphalt mixes release similar, if not lower, microplastics amount compared to these two benchmarks. And therefore, if we incorporate recycled plastic in roads, it'll not release more microplastics than the commercial polymer modified asphalt that are already being used to make roads. I will now hand it over to Dai, who is going to talk to you about the recyclability of this asphalt mixes.
Thank you, Marie. Good afternoon, everyone. I'm going to talk about the future recyclability of plastic modified asphalt concrete. So the member,
sorry, Di, just before you go on, would you like to turn on your camera?
Yes,
That's
can you see
it.
me now? Thank you. Yeah, sorry for that. Okay. So again, the main purpose of this study is to answer the question, is plastic modified asphalt fully recyclable at the end of its service life? And however, we also ask ourselves, do we even have plastic modified asphalt that has reached the end of the service life? And can reclaimed plastic modified asphalt pavement, we call PRAP, be reused as conventional reclaimed asphalt pavement material, we call RAP, at the end of its service life? So today we're going to find out the answers for this question. So this study includes 5 main steps. The asphalt mixes were first chosen to produce RAP and PRAP, and then the RAP and PRAP were produced in lab condition. After that, the asphalt mixes incorporating 30% of RAP and PRAP were produced, and then samples were prepared for mechanical tests and environmental tests. So in this study, we use 5 different asphalt mixes with 5 different types of RAP and PRAP, and all asphalt mixes use C320 bitumen as a first binder. For RAP and PRAP, we have one RAP from hot mixes 320 as a control RAP, and another one from A35P as a reference RAP. So for PRAP, there are 3 types. One is from the dry method, one is from the wet method, and one is from the mixed method. So the production procedure of RAP and PRAP include 2 main steps. So just be noticed that because of the limitation in presentation time, so you are encouraged to read more details of these procedures in report A3A. So in step 1, the loose mix was produced, and then the loose mix was aged in the oven for 12 days at 95 degrees Celsius. So to allow the homogeneous aging, the maximum thickness of the loose mix in a tray was kept at 14, and 14 is the nominal maximum aggregate size of AC14, and which is and the parameters or the assumptions was used to determine the time and temperature, include the weighted mean annual pavement temperature of 24 degrees Celsius of Melbourne, the surface temperature, the surface asphalt layer of 35 mil thick, and to simulate the field aging of approximately 10 years. So in the step 2, step 2 was started when the aging procedure was finished, and the loose age mix was crushed using the Los Angeles machines. So several trials were conducted with different revolutions using 12 steel balls for crushing of the loose mix. And after each crushing trial, the binder was burned off in the furnace and the aggregate gradation was checked. So if the wrap gradation passed the threshold, the crushing protocol was chosen, and then the wrap was used as the final wrap for the next step. But if the wrap gradation failed to meet the threshold, and then the trial continued by increasing the number of revolutions in the Los Angeles machines, and similar step will apply again until the gradation of wrap met the threshold. So we can see here two pictures. The top one is from the wrap produced in RMIT lab, and another one is from the field. So visually, they look quite similar. So the lab produced wrap was checked for its extracted binder and the gradation. So as we can see here, from the FDI binder test on wrap, it shows the jump in the peaks of carbon oxide and sulfur oxide of the wrap binder compared to the neat binder. And looking at the carbonite and sulfur oxide index, we can see the significant increase of those index compared to the neat binder. So this result indicates that substantial aging curve in the wrap binder via the proposed aging protocol. So we should be noticed that the lab aging protocol chosen in this study was aimed to simulate 10 years of aging in the field. So for the wrap gradation, so we collected the gradations of field wrap with the nominal aggregate size of 10 and 14 mils from contractors across Australia and New Zealand, and used them as the references. As you can see here, grade curves. And the wrap curve is the gradation of wrap produced in RMIT lab. So the wrap curve falls in within the range of the reference curves. So for that, this wrap gradations was used for further step. So with the final wrap gradation information, and they are incorporated with the natural aggregate to produce the final aggregate gradations of asphalt mixes with 30% of wrap and peer wrap. So with the mix design ready, the loose mix asphalt is now produced, and the asphalt samples were prepared for mechanical and environmental test. So the first investigation, we look into the compactability of asphalt mixes. So this test aims to evaluate the densification behavior of asphalt mixes under certain compaction energy. So during the compaction, the sample height is reduced because it gets denser. So as we can see, the incorporations of 30% wrap and peer wrap did not show much difference before 100 gyrations. But after 100 gyrations, there was a deviation in the densification behavior, and they are mainly affected by the source of wrap and peer wrap used in the mix. So, however, in overall, the inclusion of 30% of peer wrap didn't show an adverse effect on the compactability of asphalt mixes compared to the wrap. So the next mechanical behavior investigation is moisture resistance. So in general, the asphalt mixes with wrap and peer wrap have a quite similar tensile strength ratio, which are ranging from 70 to 78%. So it should be noticed that the minimum requirement by Australia and New Zealand standard is 80%. So that is this result was obtained using the mixing protocol in which the natural aggregate was hit at 185 degrees and the wrap and peer wrap was hit at 95 degrees Celsius. So after that, we decided to increase the mixing protocol, the mixing temperature by increasing the preheating temperatures of RAP and PRAP to 150 degrees, and we found that the tensile strength ratio increased to 80 and 85% for 30% PRAP mix and 30% PRAP dry. So it means that the mixing temperature is very important when we incorporate high percent of RAP and PRAP. And the result in this moisture resistant test also indicates that the addition of PRAP mixes resulted in similar moisture resistance compared to conventional RAP. So next we look into the fatigue cracking. So the test was, the sample was run at different strength levels, and the strength and the results of the strength level and fatigue life was used to build the fatigue curve as in this figure. So the value of the strength at which the beam reached the fatigue life of 1 million cycles is called epsilon 6, and the value of epsilon 6 was used to compare the fatigue resistance of asphalt mixes. So as we can see here, the 30% PRAP dry and 30% PRAP mixed show higher epsilon 6 values than the 30% of RAP from conventional RAP, as it was about 13 to 20%. So among the mixes, 30% RAP from A35P demonstrate the best fatigue performance compared to other mixes. And also, we got 30% of PRAP wet have a slightly lower epsilon 6 than the conventional 30% RAP from hot mix C320. The reason behind that was, if we recall the report 2, the 30% of RAP in wet method was produced with the fresh spider C170, and the result of the mix with C170 have the epsilon 6 slightly lower than a hot mix C320, and it could be inherited from that result to RAP, and it led to the results of 30% of RAP wet method was slightly lower than 30% RAP hot mix with C320. So the next mechanical behavior we look into is rutting resistance. So the test was run at 50 degrees Celsius. The loading rate of 52 passes per minute. So during the test, the rut depth and the number of passes was recorded, and we use the values of the rut depth at the end of the test, which was 20,000 passes, as the indicator of rutting resistance, and to compare between the performance between asphalt mixes. So in general, we can see here the 30% of PRAP mixes shows an improvement compared to the 30% of RAP with C320. It is again in the case of 30% PRAP wet, because the PRAP was produced with C320 modified with 2% of plastic. So the original results of C320, C170 asphalt mix, the rut depth was around 9 millimeter. So the result here shows significant improvement in terms of the rut depth for this asphalt mix. So in terms of the emission test, the aging process of bitumen in RAP can increase the overall emission compared to the virgin material, as we can see the results from VOCs and PAH here. So that is the results of the fresh asphalt mix, and these are results of the asphalt mix with 30% of PRAP and BRAP. And similarly, in the case of PAH result, And no significant differences can be observed in the use of reclaimed asphalt, plastic modified asphalt, PRAP, compared to regular RAP in terms of overall VOC and PAH. In terms of microplastic release, as we can see here, asphalt containing RAP produced quite from plastic modified asphalt doesn't release more microplastic than the asphalt containing RAP produced from conventional polymer bitumen. And interestingly, we have the RAP produced from the dry method plastic modified asphalt release more microplastic than the fresh encounter, as we can see here. So for all the overall, it is concluded that so in this study, a methodology was developed to produce RAP in the laboratory condition. And the methodology can be used for future studies on recycled asphalt materials or to control RAP field variability during lab testing. The densification behavior or the compactability of asphalt mixes with PRAP was found not adversely affected by the presence of plastic compared to a standard hot mix with RAP. And the moisture resistance of asphalt mixes containing PRAP was found similarly to that of the hot mix with RAP. And we also found that the mixing temperature was crucial, and it was found effect the moisture resistance of asphalt mixes with RAP with high RAP content, regardless of the use of plastic. So, and in overall, the inclusions of PRAP didn't have an adverse effect on the cracking and rutting resistance of asphalt mixes. We also found that the asphalt mixes containing PRAP do not produce higher levels of emissions compared to the asphalt mixes with conventional RAP. And in terms of microplastic, it was found that the asphalt mixes containing PRAP also did not release more microplastics than asphalt mixes with RAP produced from commercial polymer modified bitumen. So for overall of this study, it is concluded that the PRAP can be used as conventional RAP in new asphalt mixes. So that is now hand it over to Filippo.
Thank you, Dai. I will just now wrap it up and present you with some summary results of the entire experimental program that lasted over the past 2 years. The first thing I would like to point out is the response to the question, is it easy to compact? And here you can see the 3 methodologies, the wet method, the dry method, and the mixed method, and you can appreciate the differences between the different densification curves, where on the left-hand side you have a wet method pretty much all overlapping with each other. Keep in mind that we only pushed this up to 2% of recycled plastics. Higher content may require the addition of chemicals to stabilize the system. So together with the advisory board, we decided not to go at higher percentages. And this is definitely the easiest to compact at the dosage used for the modification. The dry method, it basically was affected by the size of the material used. So the dotted lines are related to the coarser fraction of the aggregates we replace with the natural aggregates, and the solid lines are related to the fine fraction of PET that we used as a replacement of sand particles, as partial replacement of sand particles. In the mixed method, that's the one we'll be looking at today. Obviously, as I said, there is a little bit of a difference between the 2 types of plastics used, and we went through a little bit of commentary around the reasons, but just be mindful that if you push that limit too high in terms of selecting not the right content, it might be quite energy intensive. Second question is it effective against rutting? Well, definitely 2 out of the 3 methods are very effective against rutting. For the wet method, even if it's a low volume of plastic that you're adding, it's quite effective from lower dosages. You can see the reduction compared to a standard hot mix asphalt mix on the left-hand side, and it becomes even more effective if you find a way to stabilize it, and therefore you can add more plastics into your binder. With the dry method, you can see that the magnitude is quite small, so there are not really great benefits in terms of rutting, not that we expected any, but I would say that minimal advantages against rutting are offered by this method. The last one is the one we've been discussing today, the mixed method, and this is probably the most promising in terms of usability in the field. There is quite a remarkable effect in terms of rutting, especially if you select the right content and the right type of plastics. We've been talking about 3 out of the 6 mixes performing better than the conventional polymer modified binder used in Australia. Is it durable in the long term? So looking at the fatigue life, on the left-hand side, again, you have the wet methods, and you can appreciate there is quite a big difference between these colored line at the bottom, which are essentially the representation of the standard conventional unmodified asphalt and the plastic modified asphalt mixes at low plastic content, all the way up to the red line, which is the A35P, so the conventional polymer modified asphalt. So at low dosages, it really does not provide any significant benefit in terms of fatigue. However, we can engineer the product and bring it up to higher level of plastics to provide a little bit better fatigue resistance. It's very good for rutting. In terms of fatigue, you really need to engineer the product. You can maybe even think about mixing and blending different polymers, and one of them being recycled plastics. The dry method, you can see that really the lines are all quite close to each other, and there is not much difference between the conventional unmodified asphalt and the plastic modified asphalt. So I would say, again, minimal advantages against fatigue. On the mixed method, that's the one we'll be looking at today. Again, you can appreciate the black and the red line as the 2 conventional unmodified and modified mix. And for the right content and the right type of plastics, that becomes quite similar behavior to that of a A35P. So there is a significant improvement in fatigue resistance as well. We have been discussing about that today. The volume of recycled plastics per lane kilometer, how much can we use on a wearing course, for instance, 1 lane, 1 kilometer. So the wet method is obviously low. We are modifying the binder, so we are adding a certain percentage of plastic to the bitumen, which is already like 4 to 6% of the entire matrix, the asphalt mix. So less than 1 ton per lane kilometer. The dry method is the one where you can push higher volumes of plastics into the mix, up to 4-8 tons per lane kilometer. And the mixed method is still high, but kind of an intermediate situation between the two, between 3 to 5 tons per lane kilometer. So that's just a quick look at the volumes that can be used. Obviously, that depends on the mix design and a lot of different other factors. Does it produce hazardous emissions at a high temperature? If you can see, I've just decided to put the same photos replicated 3 times for the wet, the dry, and the mixed method, and that's because none of the 3 methods really produce higher emissions than conventional asphalt. Yongjia has presented these results to you today, but also in previous webinars. In general, polymer modified bitumen was found to reduce emissions compared to unmodified bitumen. Does it produce microplastics? Again, the 3 photos are kind of the same because all the 3 methods produce a comparable level of microplastics to conventional polymer modified asphalt. So we found very similar levels, and that's why you can see the 3 photos are actually the same. So if you're asking what type of plastics can you use in asphalt, well, I would suggest that you go back 1 step and look at report 3A. The one that we are presenting today is report 3B, especially appendix B, where there is a proposal for the characterization of recycled plastics to be used in bitumen and asphalt mixes. This is kind of a characterization of the plastic itself. So it's something that maybe if you are a plastic supplier, you may want to have a look at, because it contains valuable information for you to validate your product and for possible uses in bitumen and asphalt. Are there any performance related or performance based specifications for plastics in roads? Again, if you go back and look at report 3A appendix C, we have developed a proposal for the performance based evaluation of bitumen and asphalt incorporating recycled plastics. This has been divided for local roads and medium to high traffic roads. There's a lot of more information and detail in the report 3A at the appendix C. We've also generated this sort of performance graphs, which are basically independent by the type of mix design, the quantity of bitumen you're using, and you just simply plot 2 of the properties you're interested in out of a few other parameters that are described in that appendix to see how your product compares with conventional asphalt or conventional polymer modified asphalt. And usually, if the plot is moving towards the top end corner, the top left corner of the graph, it means lower rutting and higher fatigue life, so definitely better. Just for your information, these points here in the graph are related to the mixes that we've been presenting you today. So the 1.5% here is the 1.5% post-industrial plastics at RLDPE. All the information can be found in report number 3, part B, for what you have seen today in much more detail. The report was published in October 2022. It is available for download at this website down there, but you should have a copy also included into the handout. That's pretty much it. I would like to thank all these guys here that have been working for 2 years on this project. And I will hand it over now to Elena.
Thanks very much, Filippo. And if all the presenters would like to turn their cameras on and join us for the Q&A, we are running a little bit over time, but we'll run questions for 10 or 15 minutes and just cover as much as we can. So over to you, Andrew.
Right, Filippo, just confirming, when you referred in the mixed method to the proportion of plastic used, that's based on a proportion based on the mass of total aggregates?
It is, yeah, that's correct.
Slide 23, Eleanor. So the results summarised in this slide are based on one type of asphalt size 14. Do you think when with asphalt mix suppliers, with their proposals, they should be required to repeat the testing for their particular mix and bitumen source, etc.?
No, as I just said, probably in the last slide, or the second last slide, with the Appendix C in Report 3A, we wanted to get out of the specificalities of each and every single mix design. So the addition of those performance graphs was actually put in place exactly for avoiding that during each and every single qualification or characterization of asphalt, we had to go through all the tests again and again and again. So if you think about that central point of the performance graph, that's what your benchmark point is. If that's your benchmark and it's used and it's like an open graded or an SMA or a dense graded or a gap graded mix with different binder content, you just follow the standard procedure for testing that and see how your particular mix design or your proposed mix design compares to that, and you provide the data to the client or to the approver or the decision maker in that case.
Okay, slide 33. Yeah, that probably doesn't match the question, but the question related to the amount of plastic used. 1.5% seems to be about the maximum that you would utilise in the mixed method. Do you see any advantages in trying to go higher?
No. Well, it's probably not related to slide 33, which is about emissions, but no, in general, we found it difficult to mix more than 2% by weight of the aggregate. Again, it's not 2% by weight of the binder, it's by weight of the total mass of the aggregate. So it is quite a lot of plastics. You have seen probably the video where Dai was mixing it in the lab, and it was pretty much all covered by plastics, even at the 1.5%. So it becomes quite sticky and difficult to compact. It becomes a bit solid as a mix, not really workable. That doesn't mean that if you go up with temperature like 190 plus, you can't still make it work. Maybe you could, but that probably defeat all the purpose of keeping the temperature down and doing it for sustainability purposes, because then at that point you will start seeing a lot of emissions coming out, a lot of energy being required at the asphalt plant as well for overheating the aggregate.
Right. In terms of assessing workability, you looked at compatibility of the mix. Do you see the potential to include a workability requirement into the specification? And if so, would there be criteria around that requirement?
In the Appendix C, and Dai can correct me if I'm wrong, in the Appendix C of that Report 3A, we have added a minimum and maximum value after a certain number of gyration. So there is a number that can relate to compactability in our proposal. That was due to the fact that we didn't want the mix to be not compactable, so that's why we ended up with the maximum limit. But also we used a lower limit to make sure that people were using something that in a way was given the right amount of void contents in the field as well, so it was not overly loaded with binders and overly loaded with the wrong type of plastic.
Okay, this question is, Dai may also have some input to this question. So you developed a protocol to produce RAP, an aging protocol, and presumably there was nothing available at Austrade's level, and therefore you looked overseas, developed a method, and just confirming, validated that method based on comparison to real RAP that you sourced from the field. Is that a fair summation?
Is it the question for me, Andrew, or?
Either Dai yourself, Filippo.
Dai, do you want me to answer?
Yeah, you can.
So we got the method from a report that was published last year in the United States, which is the summation of probably 4 or 5 years of experimentations on this. We have adapted to the Australian conditions. Obviously, we wanted to validate it against the available RAP in Australia. That's specifically for the crushing and the similarities between the gradation from a real field RAP with the gradation we got after that Los Angeles crushing process, part of the process. It would have been much easier to just age the asphalt loose mix and put it back into the asphalt, but that's not really similar to what's happening in the field, where you need to take it off the road first, take it out of the road first, bring it back to the plant, crushing it, and then reusing. In terms of the differences that we've found when extracting binder from field RAP compared to our artificially aged RAP, there were differences in there. In fact, if you remember the slide on the FTIR, there were 3 different bars, and the sulfoxide and carbonyl indices on the field age RAP were higher than the artificially aged RAP. Now, our method was aimed to simulate, and of course, this is not going to be accurate 100%, but it was aimed to simulate 10 years, approximately 10 years in the field. However, we have no clue about how aged was the RAP that we sourced from one of the contractors, whether that was 20 years old, 25 years old, 30 years old. And in the field, you don't have just the thermal aging that we have provided in the lab. You also have UV aging, you have moisture related aging, so on and so forth. So obviously we were not expecting the 2 binders to be exactly the same, but we used the procedure as a comparison between a lot of different mixes, and that was kept constant. So pretty much all the other mixes were aged according to the same procedure. So yes, to answer your question in short, it was a fair summary.
No worries. Again, in terms of compactability issues relating to the mixed method, you indicated that I think at concentrations greater than 1.5%, there's likely to be compactability issues. Has there been any field validation work undertaken to assess compactability?
No, this project was mainly related to a laboratory assessment. 2 years ago, there was pretty much nothing related to microplastics emission, fuming, and the use of plastics in general. What type of plastic should I use? What type of plastic should I not use? So these 2 years, we focus on the lab work. There is an intention now to develop a plastic asphalt trial or demonstration project in Victoria. And that's probably a good occasion to verify all the mix designs and the claims that are in this report.
Okay. Thinking about warm mix asphalt technology, is there any particular concerns relating to the use of that technology with utilising RAF that contains recycled plastic?
It's difficult to answer yes or no just because we haven't tested it. But if we're using warm mix asphalt technologies with other polymers, whether it's SBS or EVA modified asphalt, I can't see why we cannot use it for other polymers, which are just recycled polymers, but they're still polymers, such as polyethylene or polypropylene. But as I said, it's difficult to answer yes or no if you haven't tested. I guess that could also be part of the demonstration project.
Yep. I think, yeah, one more question. So thinking about the 3 methods that have been investigated, any comments on the relative cost per method?
WEF method, the cost of recycled plastic, depending on the quality and the source you selected from, can be anything between 50, 60 cents per kilo all the way up to $1.2, $1.3 per kilo. If you compare that, and we just use 1 and 2% of it, if you compare that with the cost of SBS, $3 to $4 per kilo, I'm not sure about the cost of EVA right now, and the usage that we and the content that we use SBS in Australia, which is anything between 4% all the way to 6%, I would say that the WEF method is still comparable in terms of costs, if not cheaper than a standard polymer modified binder. When it comes to the dry method, that becomes more expensive because in that method we are substituting something which is natural aggregate, basically fine sand and coarse aggregate that you can probably get between $4, $15, $20 per ton, with something that you can get for $100, $200 per ton. So that becomes more expensive, but you're using small contents, 0.5, 1, 2%. Again, there might be sources of plastics that we haven't been able to investigate in this project where you can get a very low price. But you need to be aware that the comparison is between the cost of natural resources like aggregates, $15, $20 per ton, with the cost of plastic. So if you're really able to get plastics for such a low price, which I doubt, then it would become cost effective. Otherwise, it will be not. Unless you have incentives from external parties, say governments, that will give you extra budget, or they will cover the extra cost for using it. In terms of the mixed method, and that's the final one, I think it makes sense because it provides a lot of extra performance. So in terms of durability, we have demonstrated how the rutting was even better than the polymer modified asphalt, and fatigue in some circumstances was also quite close to that. So if you think about the cost of the polymers and the not problematics, but the complexities of handling polymer modified binder compared to just using recycled plastic directly into the pack mill at the asphalt plant, that probably will save a little bit of time and energy and a lot of extra steps. So I can still see cost efficiency in the mixed methods.
Okay. All right. Noting where we are with time, Eleanor, we might draw the questions to a close and hand back to you.
Thanks so much, Andrew, and thank you, everybody. It was a great session. Thank you to all the audience for sticking with us through that slightly delayed presentation, but really, I think, great information. So just in terms of what we've got coming up, I won't go through these in any detail, just to say that we've got a few sessions left this year, but probably of most interest to this audience will be a session that's coming up next year, which isn't on this list yet, which is looking at the incorporation of recycled tyres, so particularly car tyres, and their incorporation into asphalt, so via crumb rubber. So keep an eye on our website for that. That's coming up next year. So thank you. Look, everybody, that was just a terrific session, and we'll close out now. Once we close up, a survey will pop up, so please do just take a couple of minutes to fill that out for us. Your feedback is always really useful and helpful. So in closing, I'll just say thank you very much. Thank you, Filippo, Young, Marie, Di, and Andrew. Terrific session, and it's just been great to have you present to us through the stages of this project, which has been, just fascinating, and I think we're all so excited about the results. So thanks so much, and everybody in the audience, stay well and safe, and enjoy the rest of your day, and we'll see you next time. Thanks, everybody.
Thank you.
Bye-bye.